Hello, and welcome to my presentation on modeling spatial and temporal emissions for animal farming using mechanistic models. My name is Martina Makagi. I'm an undergraduate student at Purdue University. I'm studying environmental and ecological engineering. The other authors on this work are Yundru Chen, who is a graduate student at Johns Hopkins University, studying biomedical engineering, and Garge Abunava, who is a graduate student at Purdue University studying agricultural and biological engineering. The PI for this work is Dr. Shweta Singh, who is a professor at Purdue University in the Environmental and Ecological Engineering Department, as well as the Agricultural and Biological Engineering Department. This presentation is for the AKI annual meeting. So to start off, some motivation behind this work. The motivation lies largely behind the impact that agriculture has on the USA's total greenhouse gas emissions. So out of all emissions, agriculture represents 10% of total emissions, according to the EPA. And within agriculture, the IPCC found that about 2.8 million metric tons of carbon dioxide came from swine farming in the year 2018. So swine farming represents a large portion of carbon dioxide and other greenhouse gas emissions, which can be harmful to the environment. Animal farm modeling dates back to the 1980s. The USDA created the Integrated Farm System model around that time, and that was used originally to simulate crop farming, but has grown to the present day to include cow farming as well. However, the model does not have swine farming incorporated into it. Historically, cradle-to-gate life cycle analysis in-field methods and predetermined emissions factors have been used to estimate greenhouse gas emissions. However, these are expensive to update and time-consuming to get these values as well. And a map of temporal emissions is not currently available and not easy to quantify at the county level. And it is necessary to quantify changing emissions so that we can develop strategies for mitigating these emissions. So largely the motivation behind this work is to reduce greenhouse gas emissions and protect our environment. So the research objectives for this project is, first of all, to develop a model that estimates temporal emissions for various sizes of hog farms. The temporal feed consumption model is needed as emissions from hog farms are dependent on feed consumed. So using the feed that is consumed by the hogs, we can estimate temporal emissions, and these results can then be used to analyze, for example, air quality in certain regions as a result of hog farming. And additionally, to show the spatial variation in the emissions for hog farms. So our approach to this work is to create a MATLAB model to simulate day-to-day hog farm operations, such as tracking the daily weight of the hogs, the daily amounts of feed consumed by the hogs, and the reproductive cycles of mother hogs. We would also like to use the model to estimate greenhouse gas emissions from the hog farms based off of the type and amount of feed consumed and the manure management system used, as it is the manure that releases these greenhouse gas emissions. And then finally, to create a temporal emissions map for specifically the state of Illinois at the county level. This is not something that currently exists, and it will be useful in showing how greenhouse gas emissions vary at the county level and how that can affect things like air quality. So moving on to the methodology for the model. To model the temporal feed consumption, I'll start you off with a little background. So the life cycle of the hogs, a sow, which is a mother hog, is pregnant for between 114 and 116 days. And for the model, we assumed an average of 115 days. On that 115th day is a farrow day, and that is when the sow or the mother hog gives birth to the litter of piglets. And the sow gets a set number of resting days and is then fertilized in order to repeat the cycle. And this amount of time is 100 days in the model. So, and then once we have that, feed consumption, manure production, and emissions can be tracked based on the weight gain of hogs on day-to-day farm operations. So specifically in the model, the way we calculated the initial number of hogs was to take breeding hogs and add it to initial input of hogs. And then we assumed that there would be no addition of hogs afterwards. The total number of hogs at a given time can be calculated by adding up initial hog inventory and the hogs produced by the breeding hogs. So that would be the litter birthed on a farrow day, once they are grown enough to be considered hogs. The value for litter rate is 10 pigs per litter. So a sow will birth an average of 10 pigs on a farrow day. And this was found using the USDA's data. It was averaged from that. The value for litter, so the number of times that each breeding hog is farrowed, is 1. And since breeding hogs generally have a life period of 3 years, we set up the model to run for a period of farming days or 1,000 days. So here's a flow chart showing how the model works. So you have your inputs, which is the feed amount, the corn and soybean ratios, which are both dependent on the farm, as they can feed their hogs different amounts, as well as different brands of feed, which would have different corn and soybean ratios. And then the number of farming days. And then the code iterates through a while loop that would iterate through each farming day. And then this little graph shows how how the weight of the hog is dependent on how much you feed it. So, and then the outputs are the array that tracks the weight of the pig per day, an array tracking the mass of the feed, soybean and corn consumption per day. So you're able to see how much feed is consumed on a given day, and at any given point during the farming days, what the weight of the pigs are. Specifically for simulating farrow days, the way we do this is the code asks, has the sow finished the gestation period? So that means, has it reached the day 115th, which is the farrow day? If yes, then it'll birth the litter rate, which is 10 pigs. 10 pigs. And if not, then it'll ask whether it is resting or not. If the sow is not at rest, then it gains an average daily gain weight, and that is added to the mass of the sow. If the sow is at rest, the weight of it does not change. So moving on to modeling the temporal methane emissions. So this was done using FAO formulas. And it's calculated based off of the daily feed amounts and the type of feed, as well as the manure management system. So the first step is to calculate the volatile solids that the manure produces. And that's done by multiplying these different values together. So some of the variables are the feed intake per head. So that's just how much feed the hog gets per day. The diet digestibility, the ash content of the feed, and the volatile solids produced from wasted and unconsumed feed, which we assume to be 0 for this model, just so we could focus on volatile solids produced directly from the hogs consuming feed. The next step is to use that volatile solid value we just calculated and multiply it by these different values, such as the biodegradability of the manure, the integrated methane conversion factor, density of methane, the fraction of volatile solids degraded by the management system, the emissions factor, and the fraction of manure handled by the manure management system. So this part focuses largely on the type of manure management system used. And for this model, we assumed a deep pit manure management system, which catches all of the manure underneath the hogs. And then this will give you the methane emissions in units of pound per hog. So the data that we acquired for the model, so for the feed consumption model, we can couple it with the Illinois data, and we can get the feed consumed, so corn and soybean as well, masses of that per hog per day, and then the weight of hogs that decide feed and market ready hogs to take out from farm. So, and then the NASS USDA's data has a hog inventory, which is the number of hogs that includes breeding and market hogs. And then coupling the emissions model with Illinois data, the emissions model output, so the emissions per hog based on the feed consumption per day, and then the NASS USDA's data has the number of hogs on a farm, and the variation of weight and age and the effect of feed is accounted for by the model. So moving on to the results. So tracking the feed consumption of the feed on the farm. So this shows how the feed, mass of corn and soybean rise as the age of the hog increases because they get fed more the older they are. So we can see that there is a peak around here. The results for tracking the hog weights. So top graph shows the weight of a single hog, and you can see how that how it increases in the same way each time. And then the bottom graph shows the total weight of all the hogs on the farm at any given moment. And that's dependent on the initial number of hogs that is inputted. This graph shows the amount of hogs on a farm at any given day. This is also dependent on the initial amount of hogs that is inputted, but you were able to track how many hogs you have on a farm at any given moment, and the model accounts for hogs that are birthed on the farm as well. Finally, this graph shows methane emissions per day. So we can see that as the days increase or as the hog gets older, it is consuming more and more feed and therefore producing more and more emissions. So in conclusion, an automated model has been developed in MATLAB that can be used to estimate the feed consumption for different hog farm sizes, the manure output per day that can be simulated, and a greenhouse gas emission output, as we saw in the results. There's a lot of potential for future work with this model. We have to improve the hog inventory data for model validation against different farm operation sizes. So right now the model is currently only working for the entire state of Illinois, but we'd like to scale it down to the county level. There's room to improve the emissions portion of the model and include energy usage in those greenhouse gas emissions, as farms do use a lot of energy to operate. And we can validate this against the national emissions inventory. Spatial emissions, we can track water usage on the hog farm. We can use the model to see how feed type affects emissions. Those variables are inputted into the emissions calculations, so you can see how that would affect it. And then we can test the model for other states and standardize it to estimate emissions from the animal farming sector. So thank you for listening to my presentation. I'd like to acknowledge the National Science Foundation's CBET program and the Purdue Summer Undergraduate Research Fellowship. They funded some of this work over the summer. Thank you.